Alright, so let's finish up what I need to teach you missing our snow days here. And what we're going to learn about is what are three intermolecular forces. Write down the I can statement. I can identify and describe the following intermolecular forces. And we're going to abbreviate intermolecular forces from now on as IM forces. Okay. First intermolecular force we're going to talk about, the most powerful one, hydrogen bonding. And here's what hydrogen bonding is, okay? Hydrogen bonding is hydrogen bonded to a very electronegative atom ends up being weakly bonded to an unshared electron pair of another molecule. Okay. Write down that definition, and I'm going to draw a picture and give you a little bit more of an explanation here. Okay. And now hydrogen bonding is what holds water molecules together, but I'm going to show you ammonia NH3 just to do something different here, but it's the same kind of concept that will happen with H2O. So what you have is you have NH3 one molecule looks like this. It has an unshared pair of electrons, and so the three hydrogen atoms there are kind of bent down in a pyramid shape. Right? So what happens with each one of these bonds is the hydrogens, you should know, become partially positive because the nitrogen is much more electronegative. Okay? So the electrons in this bond here hang out more by the nitrogen and not at all really by the hydrogen. And so when that happens, hydrogen has that partial positive charge. So what a hydrogen bond is it keeps two of these molecules together. Alright, it'll be much more than two, but we're just going to show two. If you have another NH3, with those unshared electrons, this positive, partially positive hydrogen atom is going to attract to those unshared electron pairs. Okay? And this right here, this attractive force is our hydrogen bond. Okay? So we got hydrogen is bonded to a very electronegative atom that's this to this, this to this, this to this, okay, ends up being weakly bonded to an unshared electron pair of another molecule. Okay. This is why it's an intermolecular force between two molecules. Now, here's the thing. This will only work with hydrogen and three other atoms. Let's write this down. The atoms that pair with hydrogen to form a hydrogen, I'll just abbreviate it, H bond, nitrogen, as we just saw, also oxygen, okay, which I told you because water does this, and also fluorine, the most electronegative of all atoms. Okay, these are the three atoms when paired with hydrogen will form a hydrogen bond. Okay, this right here is the strongest intermolecular force. There's actually some debate about calling hydrogen bonding an actual bond. Okay, it's much weaker than our normal covalent bonds, and to me it keeps two separate molecules together, so I don't really consider it a bond. I consider it an intermolecular force, but it is the strongest of the three that I'm going to show you today. Okay. Now I just wanted a couple things about why this happens. Okay. Why does this happen? There are two reasons here. Number one, the hydrogen is so small. Wait, is that where I want to start? I'm going to say number one, the electrons are located near the electronegative atom, nitrogen, oxygen, or fluorine, so often that hydrogen is always very partially positive. Okay, that's the first thing. Right? You have to have these very electronegative atoms. Okay, so the electrons in the bond are always by them, never by hydrogen. Okay, and here's the other key component. It's the fact that hydrogen is so small. It doesn't have any shielding between its valence electrons and the nucleus. In fact, once those electrons are away from the hydrogen, there really is no valence electrons. So we can say there is no shielding electrons in hydrogen. So its positive nucleus has a strong liking for, a strong attraction to the unshared electrons. Okay. It really, really likes these unshared electrons that the other NH3 molecule has. So that's right there is where your attraction is going to be. And because of this, number two, that's the reason why hydrogen is going to be the only atom that does this. Okay. All the other atoms are going to be too big, and so these shielding electrons won't make that attraction quite so much. Alright, so that's hydrogen bonding. Let's move on to the next type of intermolecular force, and that are called dipole-dipole attractions. Okay. And you already know what the term dipole means. It means you got a molecule where the opposite poles are partially positive and partially negative. Okay. And what dipole-dipole attractions are attractions between polar molecules. And you really, these are the main attractions, the main intermolecular force between polar molecules that don't do hydrogen bonding. Okay. And here's the thing, this is an easy picture to draw. It's as simple as this. Let's say you have HCl. Okay. One HCl molecule. The hydrogen is partially positive. The chlorine is partially negative in that bond there. You have a polar molecule, that's the only bond there. One end is partially positive, one end is partially negative. And the way these things stick together, between two of them, that right there is the intermolecular force, your dipole-dipole attraction. And as many as you're going to have, that's your intermolecular force. Right here, right here. Okay? Opposite charged poles attract to each other. Okay? And we know HCl molecule does this because HCl is polar, but chlorine is not one of those atoms that is electronegative enough to form a hydrogen bond. So the type of attraction that keeps HCl together is called a dipole-dipole attraction. We'll label this second strongest intermolecular force. Alright. Last one we're going to talk about are called London dispersion forces, and these things are kind of crazy. Just wait till I show you how this sticks together. Alright, and here's what London dispersion forces. These are forces that happen because electrons in covalent bonds constantly move. Okay. Electrons in covalent bonds stayed still and never moved. London dispersion forces could not happen. Okay. All molecules have these attractions. Here's the key thing, even nonpolar molecules. So out of all the different intermolecular forces, this is the only force that keep nonpolar molecules together. Okay. Last point about this before I draw you a picture, this is the weakest. So what I showed you goes from strong to weak intermolecular forces here. So the example I want to do is fluorine gas F2. And so what I want to show you is this. Picture two F's joined together with a single bond just like that. Okay. And these electrons here are constantly moving. Sometimes they're there, sometimes they're there, sometimes they're there. Okay. What happens is every once in a great while, these electrons will go and they will both be on one side of your molecule. So for a split second, you have a partially negative end. For a split second. And so for that split second there, the other end, okay, becomes partially positive. Alright. So now the way F2 would stick together, okay, let's say you have another F2. Okay. And then the electrons here are constantly moving in the bond, and maybe now they are both over here for a split second, and this end becomes partially negative, and for that split second the F2 becomes partially positive. And so what you end up having, okay, is an attraction right here between your partial positive and partial negative. Okay, doesn't happen long, but it happens long enough for these molecules to stick together. These momentary attractions can, not always, can keep molecules near each other. And this is why more often than not, these type of molecules that are nonpolar, they're going to be gases. They're not going to come together and form solids or liquids because they just aren't attracted to each other. So this is what a London dispersion force, it's kind of crazy. You're talking about split second attractions because those electrons are always moving. Every great once in a while, one end of the molecule becomes partially negative and the other end is partially positive.